This tutorial looks at feedback for high order systems with a focus on proportional feedback. Just a reminder, hopefully you've looked at the previous tutorials and you're familiar now, but we expect you to understand the basics of feedback, and this tutorial is asking how does a simple feedback affect the closed loop behavior. And here we're going to look at high order systems. Now, because they're high order systems, it's difficult to do the calculations on pen and paper, and therefore we're going to focus on the use of MATLAB, which we think is what you would normally do in a job. Now, some other reminders: read the questions and try them yourself before you look at the solutions. And the way to do this is to pause the video after you've read the question and try the answer before you continue with the video to look at the solutions we have provided. Some background, just a reminder, we're looking at open loop systems having a transfer function relationship like this, y equals gr, whereas if you put g in feedback with some compensator m of s, you end up with a closed loop relationship, something like y equals gm over 1 plus gmr. And the question we're asking is, how does this closed loop relationship change as I change m? Question 1. A system G and a compensator K are connected with unity negative feedback. Use MATLAB to 1. Determine the closed loop poles, 2. Determine the closed loop gain, and 3. Plot the closed loop step responses. So this question is based upon core skills. You'll see G is given here, it's third order, and K is given here. Now's the time to pause and try this yourself while I move to MATLAB to show the solution. First then, let's enter the G into MATLAB. There it is, 0.01 over s cubed plus s squared plus 0.1s plus 0.02. Next, enter the chosen value of k is 2, so you'll see I've done GC1 to give the output transfer function g times 2, and GCU1 to give the transfer function to the input. Next, let's calculate the poles. I'm using PZMap, that's typical MATLAB command, so you'll see there's no closed loop zeros, and the open loop poles, here they are, minus 0.9389 and minus 0.03 plus or minus j.2. So it's pretty much underdamped here. You'll see quite a large imaginary bit compared to the real bit. Closed loop gain I can get using this bode command, bode frequency of 0, closed loop gain 0.5. And finally, you're asked to do the plot. So there's the statements we use. You'll see we've used step, GC1, GC2, and you'll see the output is this blue plot, very oscillatory, slow to settle, as expected because we saw the closed loop poles had a large imaginary part, and the input also oscillatory, starting at 2 because k was 2. Second question. A system G is connected with 3 alternative choices of feedback. So you'll see K1, K2 or K3, where the values are given 0.1, 1 or 10. And here's my G of S. Compare and contrast the behavior with these different choices and comment on what happens for large K. And the key thing is we're expecting you to use MATLAB, because to do this on pen and paper would be very difficult. It's a third order system. So if you pause now, I'm going to move to the answer. So let's scroll down here, and you see first, enter the G. There it is, 1 over s cubed plus s squared plus 3s plus 1. Now we had 3 different values of k, so I've defined GC1 to GC3 to represent the closed loop transfer functions for input and output for those 3 different values of k. You'll notice I've just entered those. I'm not going to read them out. You can pause the video and see the statements if you need them. So first let's look at the poles. For the first choice, k equals 0.1. There are the poles, minus 0.3, plus or minus j 1.63, and minus 0.4. Stable, but oscillatory. Now with k equals 1. What do you notice? Again, stable, but oscillatory, and more underdamped than with K1. What about with the third choice of K, which was 10? And here you'll notice we've got a positive real part, and therefore you are closed loop unstable. Let's look at the two gain statements for K1 and K2. So you can see with K1 a gain of only 0.09, with K2 0.5. It makes no sense to look at the gain with K3 because we're closed loop unstable. And now let's plot these. So again you'll see I'm only plotting the step responses for K1 and K2 because with K3 I'm going to be divergent. And you'll notice I've used subplots so I can see the inputs and outputs in the same figure window. So there we go. K1 you have this dark blue plot. You'll see it's relatively smooth but settles at a very low value, a big offset. Whereas if you look at the green plot, which is K2, very oscillatory, and that's what we expected from those pole positions, not particularly fast to settle at all. And you'll see a similar pattern replicated in the input plot. So what happens to a large K? We've dealt with that. You saw that as K increased, we went from stable, closed loop behavior, to unstable. We went from smooth behavior to oscillatory to unstable. Question 3. A system G is to be connected in feedback with a proportional compensator M of S equals K. And you'll see G has been written here. It's a fourth order system. Use MATLAB to determine a suitable constant compensator which gives a balance between steady-state offset, speed of response, overshoot, oscillation, and settling time, and for what K is the system closed loop unstable. So let's see how we might use MATLAB to do this. So first what I'm going to do is enter my system. There it is. So you see G is 6s plus 12 over s to the 4 plus 5s cubed plus 6s squared plus 2s. Now the first thing to notice is that this system includes an integrator, and therefore as long as it's closed loop stable, I'm going to write this, and hopefully not delete, you should get no offset, but the key point, that's only true if you are closed loop stable. Okay. What did I do then? That figures, we've created a new figure. Right, so first then, let's do our statement. I've put K equals 1 just as a try. Now remember, we said use MATLAB to investigate the balance between things like overshoot, speed of response, etc., etc. So what I've done is I've just put in a K and I've said, give me the step response. Let's see what it looks like. So let's go to the window. What does it look like? Now I'll make this window a bit smaller so we can see things together. And what do you notice? Unstable with K equals 1. So let's try K equals 0.1. And what do we see now? A little bit better. Okay, overshoot, perhaps a bit too big of an overshoot, but settles not too bad. So let's try a smaller K, 0.01. And what do we see now? Very smooth response, no overshoot at all, perhaps a little bit slow. So why don't we try 0.02 and see what we get now. Again, no overshoot, but it's getting faster. You'll see that from the time scale at the bottom of the figure. So we could try 0.05. And what do we see now? Some overshoot, not really big, perhaps a bit bigger than you want, and a faster response. So where are we getting here? You'll see with a very simple trial and error, just messing about in the command window, I can get towards a K which gives me the balance that I want. And that's the key thing for you to discover, that you can use MATLAB very quickly and very easily to find roughly what the solution should be. Now we also said find the K which makes you closed loop unstable. So I'm going to use PZMap for this. So you can see, let's get rid of, it's not going to let me. You can see I've used PZMap, feedback G times K, 1, and I've started with K equals 0.05, and what do I see for the poles? They're all in the left half plane. So let's try K equals 0.1, and what do we notice? All the poles are in the left half plane. So let's try 0.2, all the poles in the left half plane. 0.3, all the poles are in the left half plane, but you'll see these ones here are getting closer and closer to the right half plane. So now let's try 0.4, and now you'll see we've got 2 poles in the right half plane. So if I try something like 0.45, you'll see again 2 poles in the, oh, didn't mean to go up to 0.45, I meant to go down to 0.35. I wondered, that was a bit silly of me. 0.35, and there you'll see we're getting very close to the borderline here, and that's probably enough for you to see the point. So a K something around 0.36 puts you on the borderline of stability. So a smaller K, I'm closed loop stable; a bigger K, I'm closed loop unstable. So we've shown you how you can use MATLAB very quickly and easily to play around and get this balance between offset and speed of response and overshoot, oscillation, settling time, etc., etc. So in conclusion, we've given a few tutorial questions linked to proportional feedback, analysis and design for higher order systems.